All right, so we're talking about physical properties here. It's Science 9, and I did copy this chart from your textbook. And it's on page 134, 135 in your Pearson, Saskatchewan Science 9 textbook we're using here. And so let's just talk a little bit about this color and luster. Sorry, this is kind of fuzzy. It's kind of a snapshot that I've zoomed in, so it's a bit fuzzy. I'll kind of read some of this. But color or luster. So the color obviously is easy. You can describe what color it is, what it looks like. The luster is, well, it's kind of how shiny it is. Luster is talking about how shiny it is. So you could say it's very lustrous. That means it's very shiny, like a brand new copper penny or something, okay, a piece of metal or something like that. Melting point, also a physical property. It's where the states change. And if you're going from a state of, let's say, solid to melting to liquid here, like in the picture, then that point, the temperature at which that happens, it's a physical property of that substance. And for water, we know that that changes at 0 degrees. We just had a little discussion about that. Boiling point is another one. That's where the state changes from liquid to gas. Density, we also talked about how much mass is packed away in the space that an object occupies. Solubility, here's one we didn't really talk much about. This is how well something dissolves. So if you put a rock in a glass of water, it will not dissolve very well, right? It does not mix up very well and dissolve very well. But if you put a spoonful of iced tea mix in a glass of water, especially if the water's warm, then it'll mix up really quickly and really well. And you can drink a nice cup of tea there, or a glass of iced tea. So that's solubility, how well it dissolves. Ductility, we talked, did we mention ductile? I think we mentioned ductile yesterday, okay. So the ability for it to be, for a substance to be stretched into a wire, yeah. So copper is very ductile, it's highly ductile. Crystal shape, okay, so if something like a quartz or some kind of, rock candy or something like that, if it has a crystal shape where the angles of the sides, the faces, the edges are nice and sharp and sort of has that crystal-y look, that's a description of a physical property. It's a crystalline in shape. Conductivity, so if electricity will pass through either a metal or a liquid or even a gas, how well that electricity passes through that substance is a measure of its conductivity. That's a physical property. Hardness, that's pretty easy. Hardness, how hard is something? Texture, kind of what it feels like. Is it smooth or is it rough? That kind of thing. Malleability, okay, so the ability for something to be pounded or bent up and not crack or break into 1,000 pieces. That's malleability. So those are the top ones. Some of those we talked about, some of them maybe we haven't, but I'll get you to refer to 135 and 136 in the future there. Okay, so we'll pick up where we left off with your notes. We did this yesterday, talking about physical chemical changes. We talked about these 3 questions, had a really good discussion. We kind of debated a little bit back and forth about this one for sure. Ashes in a fire, is it the same stuff as wood? And we talked about yesterday that when you burn something, you actually add oxygen to it. That's what burning is. And so when you burn wood, it's like, well, that ash is still wood. Well, actually, it's something new because oxygen has now combined with the wood, and so we have something different. If something sours, we have something different that tastes bad in there. So these are, chemical changes. Physical changes would be like melting or cutting or something like that. Okay, so this is where we left off. What is a physical change? So your notes in front of you there, if you have those, we're going to fill in some blanks for you. And a change that affects one or more of the physical properties of a substance is what a physical change is defined as. So a change that affects one or more physical properties of a substance. So if you cut up a piece of wood, I don't know how many of you went camping this summer. Anybody go camping? Okay, now when I was your age, it was my job to chop the wood. I love chopping woods. You get the big axe out there, and I love seeing that wood split. It was so great. That was my job. And now as a dad, I realize that it's just because, dads are kind of tired and they don't want to do it. Just let the sons play around with the sharp object. Anyways, so my son does it now for me, but I did chop some wood this summer. And of course, when you break a piece of wood in half, that's a physical change because we're not actually creating something new. You don't chop a piece of wood and then it all of a sudden turns into Jell-O. right? I wish, yeah. I'd rather eat the wood than burn it. I don't know. It depends, I guess. Yeah, Jello. Turning wood into Jello would be kind of fun, I guess. If it turned into something like, I don't know, like bacon or something. Now that we're talking, that'd be great. But if we just cut something, it's a physical change because it changes a physical property of the size of it or the shape of it, right? Those are physical properties. So the key is a new substance is not formed. There is no new substance formed in a physical change. So, if we're talking about melting, boiling, cutting, right? Something like that. The substance also keeps its identity. That's another thing. So again, if we're talking about the wood, if we throw wood into the fire and it becomes ash or ashes, it's something very different. So that's not just a physical change. There's something chemical happening there. So some more examples of physical changes would be things like melting, freezing, evaporating. Now, evaporating is interesting. There's a difference between boiling and evaporating. We won't get too much into that in this course, but evaporating is similar to boiling, except it's not necessarily at the boiling point. Like it's liquid going into the gas phase, but it's not because the temperature is raised to the boiling point. It's kind of like on a dry day, the water on a lake or on a pond, some of those water molecules will escape into the air because it's super dry in the air, and they will actually escape up into the air, but it's not because the lake was boiling, it's just evaporating. So moisture from liquid state kind of goes into the gas state because of things are dry. Yes, humidity is literally water in air. So if you have high humidity, there's lots of water molecules that are flowing around in the air. Yeah, and if it's very dry, low humidity, very dry, that means that there's not a lot of water molecules in the air. And so low humidity can affect wood, like your wood floors in your house. They will start to crack or bend a little bit. Too much humidity, there may be some water droplets from the air, like actually coalesce or condense on your walls or on the floors, and mold might happen. Okay, so dew on the ground, exactly, yeah. So when the temperature drops at night, the moisture in the air, the moisture, the water molecules that are in the air, because it cools down, they kind of like bump into each other and kind of stick to each other a little bit, and they fall, and they kind of fall on the ground, and that's kind of dew in the morning.
Winter when it's cold out and it's warm in your house?
Yes, exactly. In the winter, when it's cold outside and warm and moist in your house, the water molecules in the air, when they touch the cold window, they'll form little water droplets, tiny little water droplets, and that's why you kind of get kind of that fog or that film of vapor on your windows. Yeah, and in the bathroom too, right? Bathroom, the mirror is really cold, and if you fire up the shower and have a nice hot shower, then the water molecules will bump into that cold mirror and it'll fog up the mirror. Yeah, very good. You guys are great. Okay, dissolving is another one. We talked about this, iced tea crystals in a glass of water, right? If you mix it all up, those particles, when they're all bunched together, you can see them in the water. But once you mix them up, all those big particles, little particles start to come off, and they all separate. They separate so much that you can't really see the particles anymore. You can just see kind of the iced tea color water, right? So that's dissolving is a physical change. It's just a group of them splitting off into little pieces. Cutting we talked about, bending we talked about, okay? Just bending something is a physical change. All right, so I am going to show you this little video here, and this is a video of ice cube melting.
Oh, I see this. This channel.
Okay, hang on. Just want to make sure we're okay. Good.
It's on a stove.
Okay, so this is an ice cube melting, and it's a time lapse. So minute 18, 19, 20. It's going pretty quick. Okay, so what are the physical properties that are changing here? Name some. Okay, water turning into ice turning into water is a physical change. What are some of the properties that we are witnessing here? Okay, we're seeing melting. So there's a melting point there. Describe melting. What are we seeing that's happening with melting? Okay, little bubbles. Yeah, there's little bubbles forming. Okay. Now it's going to go backwards here. It's kind of cool. What properties are we seeing? Change of what? Shape? Change of state? What else? Change of hardness. The ice cube is hard. Water is not hard. Right? What else? What's Look at your page there. What else can we see that we're changing?
It could be bent, like it's bending.
Oh, come on. What's happening here?
No, it's not solid, guys.
Bending? No, not I don't think bending. Is the texture changing? Ice cube has a different texture than water, a different feel? Okay.
The temperature.
Sorry?
It
The taste. Taste. Is taste a physical property? Well, we're not. Yeah, no, I don't think taste would be how the substance interacts with your mouth, and yeah, I don't think we'll go taste. Plus, we won't taste anything in the lab, right? If we do a lab, but don't eat or drink anything. Okay, thank you. But yeah, no, we'll probably stay away from taste. Another one?
Would it also fit with conduct?
Conductivity. Okay, well,
Because like
yeah.
water conducts electricity.
Okay, that's a great question. What about conductivity? Now, we weren't able to see conductivity in that video. If we were to actually pass some electricity through, we could probably compare the conductivity. That's a good point. And does water conduct electricity different than ice? I like that a lot too. That's a very good question. So I'll let you think about that. Maybe you can research that. But we didn't really see conductivity just in that. But that's a very good thought. Yeah, another one?
The like translucent.
Okay.
Translucent.
Okay.
The ice was more of whatever. I forget what it's called.
Yes. Okay.
And then the
So if
water
light can
is-
pass through, okay, so that a description of how light passes through, okay, so that's very good. Would that be texture, hardness, melody, bleed? I like that. Water would be more transparent than ice, right? Ice would be more translucent, right? So kind of like you can see kind of things behind the ice cube, but it's pretty fuzzy, and so yeah, so how light passes through. I like that. And that's because of the structure of ice versus the structure of water. The molecules are closer and further apart, and how they're bonded and
Why
stuff.
are some ice cubes like white and others are
Yeah.
like white?
Yeah. That's a good question. Why are they, I mean,
Just
it
the one
depends
in
on what
video
the,
that's, like, not even see-through. It's like a
yeah, I think it depends on how fast it freezes sometimes. It depends on what the quality of the water is. It depends on what else is in there. The temperatures, and like I say, how fast it freezes and what temperature it actually gets to, and things like that. And the purity of the substance. Okay, good question. Yeah, another one?
Did you say texture already?
Yeah, we said texture, yes.
And then I was thinking identity because it's changed from ice to water.
Okay, now, identity, okay. Okay, thanks for saying that. Now, you said identity or the name changes. Now, if the identity changes, that's a chemical property, a chemical change. Now, when we say ice versus water, those are just words we're using for the different states. It's still water. It would be like liquid water versus solid water. So even though we have a different name, I'm glad you said that, it's still a physical property, that melting, the change of state, even though it's a different name. It's still water. We want to focus on that.
So identity would be like.
All right, moving to chemical changes. A substance is changed into a new substance when there is a chemical change.
new or different.
Yeah, new. Yeah, new. I think that's not new. Different. New, or let's make that or new or different properties. New or different properties. And so I guess the highlight here would be a new substance for chemical change, new or different properties, and a new identity or a new name. Okay, so wood turns to ashes. Definitely different substance there, different properties. Okay, wood and ashes are quite different in a lot of ways. So we have a new substance there. Flour and water and sugar and whatever else you do to make muffins. Muffins are very different than all of that stuff just mixed in a bowl, right? So there's a chemical change that's happened there. Okay. We just mentioned some examples. What are some other examples of chemical changes that you can think of? Go ahead, just shout them out. Okay, there. Yeah, you do have some in your notes right beneath that in the page. What?
Sand into glass.
Sand into glass. Okay. That's a good question. Okay, sand and glass, very different, very different properties. So yeah, glass is largely made of sand, like a silicate.
When you blow
Okay.
oxygen into the fire.
Blowing oxygen into the fire. Well, burning would be a chemical change. Yeah.
Like when a car rusts.
Yeah, rusting of a car, exactly. Okay, now we do have some on the page here. If you look down, in your notes there. Cooking was mentioned. We talked about that. Burning and rusting. So those are great examples. Had to get the bacon here in the diagram there. So there's new substances being formed. Even like toasting bread. Like that's a tough one. Students are often like confused about that one. If you put bread into the toaster and you heat it up, if you leave it in there too long, you're very sure that there is some new substance, right? That the black charred piece of the part of the toast, right? So even making toast is a chemical change because there's something new there. Yep.
Wouldn't turning like leaves into paper be a chemical change?
Sure. Yeah. Turning wood or leaves, yeah, wood into paper, making paper for sure.
How did they make paper?
Good question. Should look that up.
What? I thought they were made of leaves.
Okay.
We got a video.
My whole life has been a lie.
I'm going to look up this video here. I just want to show you a little bit of this video. I just thought it's another kind of cool time-lapse one. Oh, wait, what?
Paper's made after?
Log burning to ash.
I think it's just.
This is the candle one.
Oh,
Okay, come on.
it's the intro.
There you go, buddy. Okay. Okay. So okay. Yes, the saying is money doesn't grow on trees.
But
Yes.
I heard like a
Not
teacher
paper.
say paper doesn't grow on trees. But, and then it said, but it does.
Okay.
That's crazy.
Our bill is
Nice
made
discussion.
out of paper.
Okay, so this is just a little video of wood burning, and as you can see, there's a lot of things happening here. You see all the soot, okay? The black ash. Yeah, we've got definitely this ash is something new. It's the wood is combining chemically with the oxygen in the air to burn and to make new things, okay?
That's crazy.
So they're pretty neat. Now, obviously, in a chemical reaction too, lots of times there's heat, okay, that is generated. Lots of times there's light that is generated. So obviously a fire would be brighter than just staring at wood and so on. Well, the wood could change different colors, yeah. If there's a color change, that might be an indication of a chemical change as well. So you can see there's red and black and white, and depending on what's burning, if there's some copper or some different metals in there, you'll see little different colored flames even. Some of you have seen those little packages you throw in the campfire and it burns all these different colors. That's just different like elements, just different things that when they burn, they show a special color. So anyways, yeah, question there?
Didn't they find out a lot of those chemicals when burned?
Okay, so this one I just thought like high school kids would think this is kind of cool. I think this is just sick. But anyways, it's a candle. It's made to look like a hand. And of course, when you burn a candle, is that a physical change or a chemical change that's happening there?
Can we watch
It's
the
it's
rusty
physical.
one?
It's physical, yeah. Look at the hand behind me too.
Can we watch the rusty one after?
My hand is burning.
Jazzy.
So I don't know. This to me is just slightly. It's disturbing. Like it's like you're burning some person's poor hand here. And I mean, like, look at what happens over time. Let's just fast forward. Look at this. It's like, there you go. Ah,
Bleeding.
even red wax. That's sickening. That's sick. Oh, poor guy. Workers' compensation. Oh.
You guys look like it's.
Oh, it's just a candle. Oh, that's sick. It's terrible. Gross. Oh. I can't stand it. My hand is numb right now looking at this video. Oh.
Oh, it's in the hand.
Oh man.
It's
Right down to the palm. I can't believe it. Oh, okay.
Oh.
Wow, can you imagine? That's torture right there. That's torture.
I think the person that made this was emo.
If any of you ever have a candle like that, I'll be super disappointed. No, I'm just kidding.
We watched the rusty
I'm just
one.
kidding.
Yeah, that's what I'm saying.
Okay.
I said that.
Okay, let's bring it in. So, did you know that when you burn a candle, it's actually the wax that's burning? The wax on the side of the candle, it's the wax that burns. Now, the wick does burn away as it goes, but it's not really the wick, the little sticky part on the top. That's not really that's providing all of the heat and light. It's the wax that's burning, and which is kind of cool. But if you look really closely at a candle, you'll see a little pool of wax, and it's that wax that actually provides the fuel for the flame. Now I'm going to show you this one as well, just a little video on rusting. This one isn't quite as gross as the burning hand that's tortured. Why not? Well, just because rusting is not as gross as burning, flesh. So it's just the way it is. I don't know, it's just the way it is. Okay, so this one on the exciting scale maybe is a little bit more boring, but here we have a boys, focus now, please. Here we have a steel bolt right here. This is steel, okay, and this is titanium, okay. So the ability to react with acid or the ability to resist corrosion would be sort of a chemical property, right? So chemical properties are how substances react with other substances.
There's yellow.
So you'll notice over time, yeah, so you see the little yellow stuff here? It's hard to tell, it'll become more obvious, but the metal is reacting with this acid to create rust.
Why is it streaking across like the?
Well, because the rust isn't sticking to the metal, it's being, like when it creates the rust, sometimes it like floats off of the bolt there into the water.
Titanium one is just.
So the titanium is pretty good at resisting corrosion, right? There's not a lot of rust here on the titanium one, but the steel bolt, you can see there's a chemical reaction happening to form something new.
How long does that take?
Well, I mean, rusting takes a long time. Did you know what? Actually, did you know that rusting is really a slow form of burning?
Yeah.
Because rusting is the metal, let's say this is mostly iron, Fe, and it reacts with oxygen to create rust. And so when your car is rusted out, or you have a bolt like this that's rusted out, really, that thing has been burning very slowly over years. So it's like a really slow burn. Like when you light a piece of wood on fire, it burns really quickly and all of a sudden it's gone. But this is kind of like a really slow burn because chemically, the chemical equation is iron plus oxygen. Just like with burning anything else, it's the substance plus oxygen. So really, it's kind of like it's burning. Like if you so when you pass a car that's rusted out, you should this is what you should do because you're a scientist and you know what's happening. When you pass by a rusted car, you should point and scream, "Ah, it's on fire!" And then just see what people do because they'll think you're crazy, but it'll be fun.
Make it rusty.
You should go outside and do that. Yeah, after school, you should go do that. If I see you in the parking lot screaming at rusted cars, I'll know why. No problem. No big deal. It's no big deal. Okay, so what are some examples of chemical changes in nature? The carbon cycle, the nitrogen cycle, and chemical weathering. Okay, so you'll learn more about these in biology as you get going. I don't know what blanks are there here. I think carbon, nitrogen, and weathering.
There's one under weather.
Carbon, nitrogen, and chemical weathering. Okay, chemical weathering. I do have a couple more blanks here that I'll explain here right now. Okay, in nature though, there's chemical changes that are necessary for life. Lots of chemical changes that happen inside of our bodies, inside of plants and animals in order for us to function properly. So you'll learn a lot about that in biology as well. But chemical weathering, I have a picture of the Statue of Liberty in New York here. And your picture is black and white, unfortunately, so that's why I have these blanks here. You can see up here that this image right here is a picture of the Statue of Liberty when it was first erected in the New York Harbor. It was a gift from France to the U.S., and the Statue of Liberty is coated in sheets of copper. And so initially, the Statue of Liberty looked very sort of brownish, almost red. Yeah. Well, it kind of looks like rust, but it's not a rusty color. It's sort of a copper penny color. But over time, reaction with water in the air and stuff like that, it turns that copper to a bluish kind of color. So this is what you see now, right? You see this kind of blue color now, but it was originally kind of a shiny, lustrous copper color. So there's definitely a reaction. I believe it's kind of a patina that is on here is what it's technically called. But on these spaces on the side here, just because it's tough for you to tell with your black and white notes here, that this is a copper color. Okay, so we'll put copper. And we'll put a shiny copper. Okay, shiny. Wow. Why? Shinny. For a second there, it was like, Whatever I wrote was going to look funny. Shiny copper. Sorry, that was like a brain. Okay, hi. Question? Yes. Wow. Bluish. Bluish? Why do these words look really strange today?
I don't think shiny's with an E.
Yeah, I don't think it's like that.
Shiny has 2 ends in it.
Shinny.
No, shinny has 2 ends in it.
Shinny?
Shinny, like playing hockey, you know, shinny? You guys never heard that? Oh.
Shiny's kind of
Bluish color. Okay.
That
Yeah.
was weird.
Why don't we just spell
It all looks weird. I don't know why those words all look weird right now. Goodness.
Name is Shinny.
Look at this. Shiny should be shiny, but then we have shiny over here. Oh my goodness. What is the reality? We need to get an English teacher in here. Okay, so the dictionary does not like this form of shiny, I guess. I don't know why. This is very embarrassing. It does like this shiny.
But Google likes the other.
Shinier. Shiniest. Look at it. Shinier has an E. Shiniest has an E. Wow.
Shinny, not have an E.
Shiny, shinily, shininess. This is terrible that we have to spend so much time on this. Well, oh my goodness. Okay, so I guess I was right the first time. I shouldn't have. Look at that. I started with no E, but that didn't look right. I know your mom's an English teacher. I know. You can ask her later. No, don't go ask her now. You can ask her later, though, compared to your homework. But we're gonna go with shiny, with no E. There you go. It's an English lesson as well. Okay, do you get the point though? Okay? Yeah, weathering? Okay. All right, grade 9s. All right. Let's get back to this second part of your notes here. Change in. Now, signs of the chemical change has occurred. Some of these are going to be physical properties. Boys, back, you listen. Some of these are going to be physical properties, but they are signs that possibly a chemical change has occurred. So, change in color. Change in odor or smell, production of heat, as in burning the log, even the smell, right? The smell of the fire, right? Color, the log is changing. Production of a fizzling kind of sound or foam or bubbles indicates that possibly a gas has been released. So if there's a gas that's been released, that is a chemical change, for sure. Production of sound. Production of sound. Now again, not every time when you see these things is this a chemical change, but lots of times this is a good clue that a chemical change has happened. And production of light.
Why is there no taste?
Well, again, we're not tasting things in the lab, so we're not going to focus on taste. If something tastes different, it's probably a different substance. So yeah, we're not going to put that down because it's not something that we can safely test. All right, let's answer these questions. Frying an egg, is that a physical change or is it a chemical change? What do you think?
Physical.
Wow.
Physical.
Okay.
I think it's chemical.
We are now listen. Shh. We're not just cracking an egg. We are frying an egg.
Oh, chemical then.
So is what you start with the same exact thing as what you end with? No. So that'd be a chemical change.
Sometimes you add butter to the pan. Sometimes you add.
Okay. No, it's chemical. Frying an egg. Yeah. Eating a fried egg is very different taste and very different visually, very different than the raw. Okay, what about shredding paper?
Physical.
Yeah, we're just cutting the paper up into pieces. The paper that goes in is really the same substance of what comes out. It's just in a different form.
Well, wouldn't
What about souring milk? We talked about that. Yeah, chemical change. We've definitely got some new stuff in there that's not good.
Didn't you say also kind of physical change because of the chunks? That would be important.
Yeah, the main change in the souring part of the milk would be chemical. Yeah, for sure. All right. So I think you should have these questions from your textbook written down. There will be some terms, there will be some little things in there that we haven't covered in the notes that you'll have to look up in your textbook. And for example, I know some of you asked me about cohesion and adhesion. Okay, so some of the questions ask about that. If you do have questions about these, you simply can't find the answers in the textbook or in the notes, please feel free to ask. But
Are these
we are, yeah, these questions are the ones that you're going to be working on from your textbook.
Could you help